Hi guys, my name is Alex, and I'm going to give a brief introduction to return-oriented programming. For the purpose of this explanation, I'm going to assume that you're familiar with this 32-bit C calling convention. As a brief reminder, right before the function foo is called, any arguments are pushed onto the stack. Right after foo is called, the call instruction will, as a side effect, push the return address onto the stack, and foo will reserve itself a new stack frame by pushing the EBP and using any extra space necessary for its variables. Now, what we want to do with ROP is we want to be able to call an arbitrary function. So here's a simple vulnerable function, and we want to be able to call the function giveShell. We can buffer overflow my variable, and we could do all we had before to return to the stack and get execution. But we want to be able to call giveShell. Now, we have this gets, and with the gets, we can have a buffer overflow, and we can put in all of the A's. We can overflow the stack with A's, and I'll go all the way up the stack, all the way into the previous function's stack frame. But we don't actually want to overflow with A's, right? There's this return address, and we want to be able to return to a specific address, not to garbage or A's. Indeed, we want to be able to return to the function giveShell, and so a buffer overflow that overflowed the entire stack frame with A's, and then overwrote the return address with giveShell would suffice here. Unfortunately, in the real world, functions are a little bit more complicated. They don't just give you a shell. Specifically, the power of ROP is that we can call arbitrary functions with arbitrary arguments. So here, we've done our overflow and we've returned to execute, but execute expects an argument. Execute actually expects more than an argument, remember? Right? Because what we've done is we've turned to execute, and we're now executing execute as if it had been called. So execute, when it's called, expects there's a stack frame above it, and expects in that stack frame a return address and an argument. We will put some fake return address there, and then as the argument, pass the string bin sh so we can get our shell. So this right here works, and we can call one function, and this is pretty interesting. But the real power of ROP is that you can call more than one function, and you can chain arbitrary blocks of code together. Consider, right, we've done our previous ROP thing, we've returned to the function call me with a 3 and passed it the argument 3, and we want to also call the function call me with a 4 and pass it the argument 4. Well, this thing that we had before, the fake return address, no longer is good enough. We want to return to 4, right? But if we just return directly to 4, then the stack frame seen by 4 will now conflict with this 3. So what we want to do is we want to clean up our stack frame and get back up to the top, right? So you see above this 3 here, we can continue overflowing. So what we want to do is we want to find a way to remove 3 from the stack, or move our stack pointer up the stack. Luckily, whenever we call a function, we can use gadgets. So specifically, whenever a function is called, all the registers need to be saved, and when right before the function returns, it needs to restore all the previous registers. Well, as it turns out, for larger functions, you can find at the very end of the function this chain of pop, 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 ret. And so what we're going to do is we're going to find a function that will pop 3 off to the stack into some register. We don't care. That register will get modified, but we don't care because we're going to continue with our ROP. And so what we're going to do is we're going to find some place in code. Note that it's not going to be the start of a function. It's going to be somewhere in the middle of some function, and we're going to return to that this offset of a function that does the pop pop ret, and we're going to pop 3 off the stack, move the stack pointer up, and return to the next thing on the stack. And indeed, what we can do is we can return to call me with a 4, and again with the fake return address and stuff. And so now look, we now have 2 functions and 2 stack frames that we can call. The really nice thing about ROP is you can call functions that aren't in your binary. Specifically, the library libc is a big, huge library with lots of wonderful functions in it. In particular, there's the function system, which you can find by just obj dumping the library itself and grepping for system. And there's also the function execve, execlp is a very nice function. And so we can return to these functions. libc is also a wonderful source of ROP gadgets that we can use to do arbitrary things we want. But libc, and we can obj dump libc to get these functions, or we can print them in GDB. So in GDB you do print system, and then that'll tell you the address of system in memory. So the weird thing about libc is if you obj dump libc and you get system, you'll find the offset from the base of libc of where system is. What you really care about is where in memory the function system is. And so with GDB you can just print that directly. You have to be careful. If libc is randomized, then you can't just print it in GDB, and you have to do something more clever. But it's not on any of the simple questions we give you. In addition, libc contains the string bin sh, which it uses to actually do the function system. And so in GDB, you can find that string in memory. And so here, let's pretend that F7EA000 is the base of libc. You can just search in memory using GDB for the string bin sh, and you'll find it. And this is really powerful, because now, rather than relying on some forced function, give me a shell or execute in your function, you can just use libc. Anyways, so there we go. That's ROP.